Hello again, this is video lecture 10.2, and we're going to start by discussing the content from chapter 10, section 2 in our book, in which we're going to continue rotational kinematics, focusing on the special situation where the object is rotating with constant angular acceleration. So in the previous video, we talked about the rotational kinematic variables: angular position, angular displacement, angular velocity, angular acceleration, and their corresponding symbols, all Greek letters, and defined them. And now, just like we did in chapter 2, after we've defined the kinematic variables, we applied them to a special case, which is pretty important: the case where the particle moves at constant acceleration, or now, the case where the rigid body rotates with constant angular acceleration. There are a set of constant angular acceleration equations. They're completely analogous to the constant acceleration equations for linear motion. So I'm going to make a table. I've done that here. And I'm just going to write down the rotational version for each of the constant acceleration equations from chapter 2. So, the first chapter here, the first column in this table here, is taken directly from chapter 2, where we talked about linear motion along an axis. Usually we called it an x-axis. And we said, what are the appropriate kinematic equations when a particle moves on an x-axis with constant linear acceleration a? The first one, just to remind you, constant acceleration equation number 1, written in a couple of ways: change in velocity equals acceleration times change in time. Delta v equals a times delta t. If the delta t, the time interval, begins at time 0, then you write delta v as v minus v initial. You write v initial as v sub 0. You solve for v final. You get this version: v final equals v initial plus at. It's just a special version of delta v equals a times delta t. What is the chapter 10 analog to that equation when I have a rigid body rotating about a fixed axis with constant angular acceleration? I'm just going to state it. All you do is take each linear kinematic variable in the first column and replace it with its rotational analog. So you get delta omega equals alpha times delta t. Again, warning, warning. The symbol I just drew a little red circle around there is an alpha, not an A. I try to write it as a pretty exaggerated symbol so that you can clearly see it's not an A. It's angular acceleration alpha in radian per second squared. So this first equation says the change in the angular velocity equals the constant angular acceleration times the change in time. If the delta t, the time interval, begins at time 0, and you write delta omega as omega minus omega initial and take the omega initial over to the other side, you get this version: omega final equals omega initial plus alpha times t. So that's constant acceleration equation number 1, both linear version and rotational version. Next, constant acceleration equation number 2, first linear version. Delta x equals v initial times delta t plus 1/2 a times delta t squared. I'm just going to leave it like that. What's the rotational version? That's right here. Delta theta, change in angular position, equals omega initial delta t plus 1/2 alpha delta t squared. So we'll use that to calculate angular displacement, change in angle, if we're given the time interval. That's equation 2 then. And the third equation that's handy, and I never need more than 3, is the one that doesn't involve a time variable, since some problems don't talk about time and don't ask about it. So the linear version is v final squared equals v initial squared plus 2 times a times delta x. What's the rotational version? Omega final squared equals omega initial squared plus 2 times alpha times delta theta. That will be constant angular acceleration equation 3. So we'll use those if we're studying rotational motion, and we know that the angular acceleration alpha is constant. Now I have a couple of comments or tips to say about this little table. First, please don't underestimate how easy it is to get confused about this table. It's very easy. Namely, it's very easy to mistakenly mix symbols from the two columns. Except for the time variable t, the symbols in the columns cannot be mixed. For example, you can't use a linear version of equation 1 mixed with a rotational version of equation 1. You can't write something like delta v equals alpha times delta t. You see, you've used a linear symbol v from equation for the linear motion, and a rotational variable alpha for the rotational. You've mixed the two columns in that table. I can only emphasize most strongly that's not going to be correct. Okay. Another thing it's easy to get confused about with these equations: units, particularly for the rotational quantities in the right column. Why? Because your book, all the books, love to give you weird units sometimes for theta and omega and alpha. They might be units like revolutions or revolutions per minute or something like that. Well, revolution is a unit of angle or angular displacement, but we learned in the previous lecture how to convert that to the SI unit, radian. So if you find yourself in a problem where you've got some weird units going on, I recommend you be safe, and the safest procedure, always with regard to units, is just to convert all rotational quantities to proper SI units. That means theta or delta theta is in radians, omega, angular velocity, is in radians per second, and alpha, angular acceleration, is in radian per second squared. Okay? All right, those are my 2 tips. Let's get right to using these rotational equations. Let's apply them to an interesting, in my mind, real-world situation, and then I'll do an example problem in class. I'm going to show you in a second here a YouTube video that somebody recorded in which they were out near the front of a jet engine. It happened to be on an Embraer 190 commercial airliner. And they recorded, this is an aviation fan, they recorded the startup of the jet engine. Initially it wasn't started, and then it was engaged with its starter, and they recorded the motion. And of course, as you probably know, a jet engine is basically a very large metal fan with a bunch of metal blades and an axis of rotation through the middle. And it rotates vertically when the plane's on the ground. And so here's what we're going to show you. I'm going to kind of describe it, and then I'm going to show you the video, and then we're going to answer some questions. So we're going to be looking at the startup, at the engine start of an Embraer 190 airliner. We're going to analyze the rotational motion of the front fan assembly of the engine during startup, assuming that it rotates with constant angular acceleration once the starter is engaged. Now, before the starter is engaged, the fan blade assembly at the front of the engine is doing what we call windmilling. All that means is it's rotating with constant angular velocity. Not speeding up, not slowing down, just turning at a constant angular rate. As you will see in a moment, the video shows that that rotation is in the clockwise sense as viewed from the front. In fact, I have a photograph here of the front of fan assembly of an Embraer 190 jet engine. And I have drawn in green dashed line a fixed reference line that I've imagined on one of the fan blades. That's going to rotate with the fan. So fixed to the fan, the engine. And then fixed X and Y axes, they don't rotate with the engine. And so the angular position of the jet engine will be denoted by the angle between that green reference line and the plus x-axis. So we're going to do the following. We're going to suppose that the figure we've got here represents the situation exactly a half a second before the starter is engaged, 0.5 seconds. Before the starter is engaged. We're also going to assume that the starter is engaged at t equals 0 when the reference line, the green line in the figure, is aligned with the plus x-axis. Notice then that this picture shows that reference line at an angular position of pi over 4 radians. So that's the angular position of the fan a half second before the starter is engaged. Okay, so let me show you the YouTube video. Okay, we're just going to let it run. First it will be windmilling, just rotating clockwise at a constant angular rate. You'll hear when the starter is engaged because it'll make a very loud sound. And then we'll watch what happens after that. Notice, it stops for a moment. Now it's speeding up, going counterclockwise. A little bit of exhaust there. Okay? All right, that's the key motion. All they're doing here, by the way, is getting it up to what they call idle when it sits on the ground. And notice how fast it's rotating even when at idle. But let me show it again. So I want to be clear. Initially, it's rotating counterclockwise at a constant angular rate, a constant angular velocity, omega. When the starter engages, you hear that high-frequency whine. And then what you observe is that the clockwise rotation very quickly is brought to rest. It stops for 1 instant in time and then rotates counterclockwise, speeding up. Okay, let's watch this again. Okay, you get the idea. Jet engines truly are amazing feats of engineering, amazing technical devices. They are very efficient. They are much quieter than they used to be. And the rotational rates at which they can achieve, they can spin, it's absolutely mind-boggling. And that they can spin at those rotational rates continuously for hours and hours and hours with almost never a mechanical failure. So I want to impress upon you, especially if you want to be an engineer, that would be a pretty impressive kind of job to have, working on jet engines. There is a plant in Ohio, General Electric, that makes and tests jet engines. And it's in Peebles, Ohio, and they do the testing there. And it's an amazing place to visit. Okay, so let's go back to analyzing that rotational startup of the jet engine. So the first question is, what is the constant angular velocity omega 0 of the engine before the starter is engaged? Denote the direction of the angular velocity by means of a positive or a negative sign and give your answer in SI units. Okay, let me give myself a little bit of space here to work. I'm going to use one of the constant angular acceleration equations. I'm going to use equation 2. Angular displacement equals initial angular velocity times time interval plus 1/2 angular acceleration times time interval squared. But I'm going to apply that to that 0.5 seconds before the starter is engaged. Remember, that's at constant angular velocity. So the angular acceleration term goes to 0 for this time interval that we're looking at. And the equation simplifies a lot, and all I have to do is solve what's left for omega. We call it omega initial. It's just the change in angle over the change in time. How much does the angle change in this 0.5 seconds? Well, it goes from where the green dash line is in the photograph at pi over 4. And remember, we're told that the starter is engaged when that green line is right up with the x-axis. That means the angle is 0. So that means theta final is 0 minus theta initial, which is positive pi over 4. So note carefully how I put the order of those terms. Theta final is 0. Theta initial is positive pi over 4. I subtract them. And I divide by 0.5. That's like multiplying by 2. That's negative. Let me write that a little bit more neatly. Negative pi over 2 radian per second. Negative makes sense because that's appropriate for clockwise rotation. 3 decimal approximation for that would be negative 1.57 radians per second. So that's the initial angular velocity of the engine before the starter's even engaged. Okay, I guess that was question 1. I should write 1. Now question 2. The starter is engaged at time 0 when the engine's angular velocity is this omega 0, which I just found. Negative 1.57 radian per second. Here comes some more information. It takes 24 seconds for the engine to reach its final angular velocity, omega final, of positive 188 radians per second. Question: what is the constant angular acceleration alpha of the engine during this startup process? I'm going to now use constant angular acceleration equation 1. Let me get this so that you can see it. Which says change in angular velocity equals angular acceleration times change in time. Let me solve for alpha, the angular acceleration. That's change in angular velocity over change in time. Again, be careful. That's omega final minus omega initial. Okay, omega final, I'm told, is positive 188 radian per second. So there we go. There's omega final. Minus omega initial. Again, be careful. Omega initial is negative 1.57 radians per second. Watch out for the signs. And I'm told that it takes 24 seconds to go from that omega initial to the given omega final. By the way, that omega final, 188 radians per second, doesn't really sound that fast. But if you do give an engineering term for that, how about 1,795 revolutions per minute, which some people call RPM. Okay, that makes it seem like, okay, 1,795 complete revolutions per minute. And that's at idle. Just to give you a sense of how fast that thing is rotating. So what is the number you get? Well, first of all, you get a positive, and you get 7.90, and that would be radians per second squared. So there is your answer to question 2. Just a little under 8 radians per second squared. That's a pretty hefty acceleration. Well, you probably noticed how quickly the angular velocity of that fan blade assembly changed. Okay, question 3. After the starter is engaged, how much time is required for the engine to reverse its sense of motion from clockwise to counterclockwise? Okay, remember that we observed that right at time 0, when the starter is engaged, the whole assembly was initially rotating clockwise. Therefore, the initial angular velocity is negative. But the angular acceleration I just found is positive. So the initial angular velocity and the angular acceleration have opposite signs. That means it's initially the whole thing's going to initially be slowing down. And in fact, it will slow down in its clockwise rotation, stop for 1 instant, and then speed up going counterclockwise, which is exactly what we saw. So I need to find the time it takes from that initial clockwise rotation at time 0 to that stopping point before it goes back around counterclockwise. I'm going to apply equation 1 again. Delta omega equals alpha times delta t. But now I'm applying it to a different interval than I did in question 2. Just the time interval from starting at the moment the starter is engaged at time 0 with the clockwise rotation to the moment where it is for an instant at rest. So for the delta omega, that means the omega final is 0. And the omega initial is omega 0. And that must equal alpha delta t. And now I'm going to solve for delta t. So notice what that is. Negative omega initial over alpha. Do your algebra carefully. That's negative omega initial, negative 1.57 radian per second. And I just found the alpha, positive 7.9 radian per second squared. Notice I'm going to get a positive value for a delta t, which only makes sense. And the number I get is 0.199 seconds to 3 sig figs. You probably could round that to 0.2 seconds and be okay. Not very long, but the video did show that it didn't take very long to change its motion from clockwise and stop and then start going back. It only takes 0.199 seconds. Okay? We're learning a lot about how this rotation works from this jet engine, just from the constant angular acceleration equations. All right, one more question. What is the angular displacement of the engine during the time interval of the previous question? In question 3. During that short time interval from the start to where it momentarily is at rest. Denote the direction by a positive or negative sign and give your answer in SI units. Okay. So now I'm going to use constant acceleration equation 2 because I want an angular displacement. I want delta theta, and that's what the second equation is about. It says delta theta equals omega initial times delta t plus 1/2 alpha times delta t squared. So we just plug in numbers. For the omega initial, plug in negative 1.57 radians per second. For the delta t, plug in 0.199 seconds. For the alpha, plug in positive 7.9 radian per second squared. For the delta t squared, plug in 0.199 and square it. Do that carefully on your calculator. You'll get a quantity with units of radians. And it turns out it's negative 0.156 radians. Negative, which you should expect because for this interval, the rotation is clockwise, and that's negative. If you're not sure how big it is, it doesn't look very big. That's just so you have a sense of it, negative 4.5 degrees. Although the proper answer would be the negative 0.156 radians. Okay? Okay, so we use the constant angular acceleration equations to analyze the rotational motion of a jet engine. I'll do an example problem, a Wiley Plus type example problem with constant angular acceleration in class. For now, I want to move on in this lecture to one more idea that it turns out is very important for future work, but takes a little getting used to. And now I am talking about the reading that is in Chapter 10, Section 3 of our book, in which we're going to relate linear and angular variables. We're going to bring the two ideas together. Let me explain why we would need to do that to begin with. Let's imagine we're looking down from above on a rigid disk, a rigid solid disk of material that's rotating about an axis of rotation that's perpendicular to the screen right through the center, coming right out towards us. There it is, right in the middle. It's marked, axis of rotation. That whole disk is rotating about that axis as a rigid body. And in fact, this arrow down here shows the sense of rotation is counterclockwise. Okay? And let me tell you one more thing about this counterclockwise rotation of the disk. Let's just say that while we observe it, not only is it rotating counterclockwise, but it's speeding up in its rotation. It's rotating faster and faster about that fixed axis through the middle. Then I know two important things about the rotational motion. Because it's counterclockwise, the angular velocity omega is positive. I know this next. Because it's speeding up in its rotation, the angular acceleration alpha must be of the same sign as the angular velocity omega. And since I already know the angular velocity is positive, I then, through the series of steps of reasoning, conclude that the angular acceleration is also positive. That's what's happening in the rotational motion. And those are the angular kinematic variables that are mostly important, omega and alpha, for the disk. Okay, here's an important tip then that I'm going to start with. The angular variables that I just talked about describe the rotating rigid body as a whole. The whole thing, every part of the disk, has the same omega at a given instant and the same alpha. So angular variables of a rigid rotating body describe the whole body. But now, let's do something else. Let's say, suppose before it starts spinning, I paint with blue paint a dot on the disk. There it is. I just marked it, that blue dot. That's a point on the disk. As the disk rotates counterclockwise, what will its motion be? Well, it will just move in a circle, won't it? And that circle will have some radius that we're going to denote by little r, which is just the distance that point is from the axis of rotation, right there. Okay? So that point just moves in a circle. And so, at a given instant, if you take a snapshot, you can ask or talk about the linear velocity v of the point. Okay? Linear velocity of that one point. It's got to be tangent to the circle pointing counterclockwise. So that's that red arrow. Now there's a relationship between the magnitude of the linear velocity of that point and the magnitude of the angular velocity of the whole disk. And that important relationship is derived in Chapter 10, Section 3. If you want to see the derivation, by all means, read Chapter 10, Section 3 in the book. I'm just going to tell you the result. It's right there. And I'll even circle it because it's important for the rest of this chapter. And it's about magnitudes, please note. The magnitude of the linear velocity of that one point is equal to the radius of its circle, which is just the distance it is from the axis of rotation, times the magnitude of the angular velocity of the disk. Okay? I'm going to take that red circle away now because I want to write some more things. So what we're doing here is we're relating a kinematic property for the disk as a whole, disk as a whole, namely the magnitude of the angular velocity, to a linear kinematic quantity of a point on the disk. Point on the disk. So we're relating a linear kinematic quantity to a rotational or angular kinematic quantity. And we'll use that formula a lot. Magnitude of v for a point on a rotating body equals the radius of its circular motion times the magnitude of the angular velocity for the whole object. Note then that if I had picked a different point, what if I had picked the point right out on the very, very edge, the very rim of the disk? I just drew it there. What could you tell me about the v and the omega for that point compared to the first point? If you need to, pause the video. I'd like you to answer that in your own mind first, and then we'll continue. All right, you see I've drawn 2 points. You can even number them. 1 and 2. 2's out on the very edge of the disk. 1 is in a little bit. Let's compare the v magnitude and the omega magnitude at those points. Note, angular variables describe a rotating rigid body as a whole. So point 1 and point 2 have the same omega. Same omega. But they clearly have different r's, right? Which point has the bigger r? The farther point, point 2. So the formula v equals r omega tells me that point 2 has a bigger v magnitude than point 1. So if I draw the v arrow for point 2, it's a longer arrow. That's the v arrow for point 2. Conversely, a point that's closer to the axis has a smaller v. That's a very important thing to realize then. On a rotating rigid body, points that are farther from the axis have a bigger magnitude of v, linear velocity. But they all have the same omega. Okay, I want to say a little bit about accelerations now. Okay, so the second picture is still that same disk and that same point that I started with, point 1, right there. But now it's going to focus not on velocity, but acceleration. Okay, now, this is important. This point, the blue that I've drawn in blue, that's moving in a circle, is not moving with uniform circular motion. What, you say? Not moving with uniform circular motion? That's the only kind of circular motion I know. Not anymore. And why not? Because the disk, remember, is rotating counterclockwise and speeding up. So that point that I'm talking about is moving in a circle and speeding up. So we don't have uniform circular motion. Oof. That means that this point actually has 2 linear acceleration components. One we're familiar with, that points towards the center. And your book now calls that the radial acceleration component, pointing towards the center. That's the acceleration we used to for uniform circular motion, towards the center. Remember we had a formula for that in chapter 4 and chapter 6? For the radial acceleration towards the center of the circle, v squared over r. Remember that? Let me start with that. Let me write it, though, in terms of magnitude. Magnitude v squared over r. That should be familiar to you, I hope. That's still true. But now let me substitute my new expression above for v magnitude. It's r times omega magnitude. So in the numerator, I have r squared times omega magnitude squared, all divided by r. Note then that one factor of r cancels, and I'm left with r times the magnitude of omega squared. Sorry, that's a little hard to see. But here's the equation right here then. That's the way we're going to tend to use it now in this chapter. The radial acceleration that I just drew there in red is given by the radial distance of that point times the angular velocity magnitude squared. But that's not all. Because that point is moving in a circle and speeding up, moving counterclockwise and speeding up, it must also have a component of linear acceleration in the same direction as its velocity, which will be tangent to the circle, counterclockwise in this case. So that's that arrow I just drew. That's a new linear component of the acceleration, and it's labeled a sub t, t for tangential component. And if you want to see there's a formula for that. If you want to see what it is, how it's derived, read section 3 in chapter 10. I'm just going to tell you the answer, but here it is highlighted. That magnitude of that tangential acceleration is given by the radial distance of the point from the axis times the magnitude, watch out for that, of the angular acceleration. Let me write it over here bigger. R times magnitude of alpha. Now, whether we're talking about the omega squared or the alpha on the right-hand side of these two equations, here or here, those are rotational or angular variables. They describe any point on the disk as a whole. But A tangential and A radial are linear, and they refer to a specific point on the disk, A tangential and A radial. So notice then, what if I took a point 2, that was out on the very edge of the disk, farther away from the axis? How would A tangential and A radial compare between points 1 and 2? You can think about that. You can pause the video if you wish. Okay, how do A tangential and A radial compare at points 1 and 2? Use these two equations I've just highlighted. Both points have the same omega and the same alpha. Every point on the disk has the same omega and the same alpha. But they have different r's. And point 2 has a bigger r than point 1. So the A tangential and the A radial are bigger, both of them are bigger for point 2 than point 1. Watch out for that. Use these formulas right here to compare A tangential and A radial at different points. Heads up, don't use that one for A radial, because V and R are both different at different points. No. Use not that one, but the one's below for A tangential and A radial to compare A tangential and A radial at different points on the disk. By the way, question for you. If this point, let's go back to this, just the point 1 that we're talking about right there, in the lower picture, if that point has 2 acceleration components, a radial component towards the center of the circle and a tangential component tangent to the circle and clockwise, what would you do if I asked you to sketch in this diagram the actual acceleration vector for the point on the disk? What would you draw? You might want to think about that a minute. Well, what we've got now is an acceleration vector that has 2 components, a radial one and a tangential one at right angles to it. So the actual acceleration vector would be along this diagonal, like so. And I'll draw the open-tipped arrow and label it A arrow. So the actual acceleration vector for that one point that I've got in blue on the disk is roughly in the direction I've sketched, not towards the center. Okay, we're going to do an example problem in class where we work with these relationships, because it takes a while getting used to relating the linear and the angular variables. But I want you to start already with a little bit of practice with these ideas. I'm going to give you a class engagement exercise for Blackboard. Sorry, let me get this back where I want it. Come on, no more. Okay. So here I want you to answer the questions that I'm about to show you for class engagement on Blackboard. And here's the scenario. We have a rigid disk that we're viewing from above, and it's rotating just as we were looking at in the previous slide. But now the disk has, at time 0, a negative angular velocity, and a positive angular acceleration at time 0. There's a multiple choice question that asks you which of the following statements is most accurate. A, the disk rotates counterclockwise and speeds up. B, the disk rotates counterclockwise and slows down. C, the disk rotates clockwise and speeds up. D, the disk rotates clockwise and slows down. You just answer that by telling me which is the most accurate statement, A, B, C, or D. Then I want you to draw pictures. You're going to have to do this on a piece of paper and snapshot it and upload it as a PDF, because I want you to draw a sketch. For the point shown on the disk, notice where it is, right there. For that point, right up there on the disk, for that point, at that instant, shown in the disk, sketch the following with appropriate arrows. V arrow, A radial, A tangential, and A arrow. You can assume that this is at t equals 0. Okay? I want you to sketch V arrow and label it, please. I better say that, huh? Just so you know, although you probably would guess I would want that. Otherwise, I don't know what arrows mean what when you draw a picture, right? Sketch and label. V arrow, A radial, A tangential, A arrow. Look back at how I did the one on the previous slide to help you. Okay? So that's what you'll do for class engagements. And then we'll do an example problem in class. So that's all for this video.